Hello everyone, today let's solve the problem police stations, right? So this was asked in the Codeforces round 408 division 2, right? So let's do one thing. You can just go through the question. It's easier to understand. I'll just summarize the question so that it will be easier for us to solve the problem, right? So let's see what the question states here. So here, let me summarize the question. So we have been given a tree of n cities, right? So we have been given a tree of n cities and k police stations, right? So we have been given we are given a tree of n cities and k police stations, right? So we have been given this one, n cities and k police stations. We have to remove the maximum number of roads. So what we need to remove? We have to remove maximum number of roads so that every city can still reach some police station within distance d, right? So we have to remove maximum number of roads, right? Maximum number of roads, so that every city can still reach some police station, right? So every this one city can reach some police station with the distance d, right? So all the roads length is equivalent to the 1. All roads length, so this one I'll just write all roads length, it is equivalent to 1. We have to print how many roads can be removed and their indices. What we need to print here? We need to print how many roads can be removed and their indices. If the multiple answers exists, then what we need to do? We have to print any valid maximum set. Again, if the multiple answers exist, then we have to print any valid maximum set. Again, I'll just read out the question loud. If multiple answers exist, then we have to print this one, any valid maximum set. So multiple this one answers exist for the test cases. Just remember this one, multiple answers exist, right? So yeah, let me write this one. If multiple answers exist, then we have to print any valid maximum set. This is fine. So let me read the question out loud. So just listen to this carefully. So we have been given a tree of n cities, right? So we have been given a tree of n cities and k police stations, right? So we need to remove the maximum number of roads so that every city can still reach some police station within the distance d, right? So again, given a tree of n cities and k police stations, remove the maximum number of roads so that every city can still reach this one, some police station within the distance d, right? So all roads length is equivalent to the value 1. We have to print how many roads can be removed and their indices, right? So we have to print what we need to print, how many roads can be removed, right? How many roads can be removed and also its index and also their indices. The number of this one, the roads that can be removed, right? So that one we have to display in the form of output along with their indices as well. Just remember this one, don't forget this one, right? And one more important thing here is, if the multiple answers exist, multiple answer might exist for the same input, and if the multiple answers exist, then we can print any valid maximum set, right? So just remember this, very simple question, right? So let me remove this one. Let me come to the input output, right? So we have been given here 6, 2 and 4, right? So just give me a second here. Yeah, we have been given 6, 2 and 4. So see here, just 1 second. Yeah, here n is nothing but the 6, 2 is nothing but here, in this case k is 2 and this 4 is nothing but d here, distance, right? N we have been given 6, k we have been given 2 and distance we have been given this one 4, and the stations we have from 1 to 6, right? So stations we have from 1, 6 basically, this one I'm speaking, stations 1, 6, and these 1 to 2, 2 to 3, this one along with the index we have to, so this one will map this one to 1, this is 2, from 2 to 3 edges, these are the edges basically, 3 to 4, this is mapped to 3, so this one 4 and this one to 5 basically, right? So here again basically n equals 6, k is 2 and d equals 4. Stations 1 to 6 we have considered, and 1 to 2 3 these 5, 1 2 2 3 3 4 4 5 and 5 6 are the edges basically, edges along with the index. edges along with the index basically, right? So just remember this one, edges along with the index. So the output that we need to get here is 1 and 5 respectively, 1 and 5 respectively. So in the question what they have asked basically, how many number of rows that can be removed along with their indices, right? So the number of rows that can be removed is 1 along with their the index of it is 5. So we can have multiple answers as well for this particular question. So I hope we are not discussing approach here. I just wanted to discuss briefly about the input output part. So what they have given and what is it, that is it I wanted to say, right? That's what I wanted to say, sorry. So here in this case now we have the idea on the question and this one input output part. Let's do one thing, let's quickly discuss the approach followed by the complexities and then let's write the code. As usual, let's discuss the approach first. So we'll be considering the same first example for the approach within the approach. So let's start let's discuss the approach first as usual. So I have considered the same first example that they have given in the question here. So here n we have been given 6, this is k, and this is nothing but here this is basically d, I believe. Yeah. So these are the edges basically, right? So the output that we need to get here is basically 1 and 5. The output that we need to get here is 1 and 5, and also we can have multiple outputs, man, right? So in the question they have strictly mentioned if multiple answers exist, then we can just go with any one this one valid path, right? So that is the thing that we can that we have to do basically. So we have to accordingly with the question we have to find how many number of rows that can be removed along with their indices, right? So here one row can be removed and its index is 5, so we can have the multiple answer as well that they have given in the question. So for this to solve this particular problem we'll be going with a breadth first search, right? BFS. So let's move on with the further things. Now let's move on with the step-by-step explanation. N equals 6, k 2 and d equals 4 we have. So the stations we have is 1, 6, right? So this one, the second line they have mentioned, right? In the first line they have given us n, k and d. In the second line they have given stations, and the other 5 lines were edges basically 1, 2, 2, 3, 3, 4, 4, 5 and 5, 6, right? Let's come to the first point here. So multi-source BFS start. So what we will do, we will put both the station nodes 1 and 6. See here, station nodes we have here is 1 and 6, right? So we'll put both the station nodes 1 and 6 in the BFS queue, right? So we are making use of the BFS, right? So we'll be going with a, quite obviously we'll be going with a queue, right? So we'll be putting both station nodes 1 and 6 in the BFS queue with the distance equals 0 and owner equals initially themselves, right? So queue initially queue will be 1, 6, arrays initial nothing but the owner of 1 will be 1, will be going with a queue as well as the owner distance and owned, right? So here distance of 1 initially it will be 0 and owned of 6, so we have 1 and 6, right? Distance, right? So here owned of 6 initially it will be 6, owner of 1 is 1, owned of 6 is 6, and distance of 1 initially it will be 0 and q initially it will be 1, 6, right? So this is fine. Let's move on with the next step. So distance of 6 is 0, distance of 1 is also 0 initially, distance of 6 is also 0, right? So I hope this part is completely clear. Let's move on with the second second point basically. So what we will be doing here, we will be expanding node 1, right? So we will be expanding, let's remove this one. So here this one we have considered distance of 6 equals 0. So we will be expanding node 1. So what we will do, we will visit the neighbor 2. All we are doing here is this one, we are expanding the node 1. What we'll do, we will visit the neighbor 2, will set the owner of 2 to 1. So we have set the owner of 1 to 1 and we are setting the owner of 2 to 1, right? So we have visited the neighbor 2 and we have set the owner of 2 to 1, and also distance of 2 remains 1 and the parent edge of 2 is equivalent to the edge hash 1, right? So we will be enqueuing the 2, or we will be adding or enqueuing the 2 basically, right? So now q becomes 6, 2. So initially we had q 1, 6. Now we have 6, 2, right? So 6, 2. Same thing we'll be doing with the this one, what do we call, accordingly with the answer that we get at the end. So q becomes 6 comma 2, right? So we'll consider 6. We will expand the node 6. So next we have this one, we will be visiting the neighbor 5. We'll set the owner of 5 to 6 and the distance of 5 to, as usual, distance is mostly 1, right? So and the parent edge 5 equals edge hash 5. So this time instead of enqueuing the 2, we'll be enqueuing the 5, right? So edge hash 5 we are going with, I have represented here. So we'll enqueue 5 here. Q becomes 2 comma 5. Q becomes 2 comma 5. The last time it was for this one, when we expanded node 1 we got 6 comma 2. When we expanded node 6 we got 2 comma 5, right? So I can just build this one and see as well, right? You can understand this one quickly if you build and if you see it in the form of figure or the diagram, right? So next what we will do, we'll expand node 2. See here we have got node 2. This time we will expand node 2. Previously we had got 6 comma 2, we had expanded node 6. This time we have got 2 comma 5, we'll expand node 2. So when we are expanding node 2, next neighbor will be visiting the neighbor, right? So here we'll be visiting the neighbor 3. This is unowned, right? So this is unowned. Owner of 3 becomes 1 and distance of 3 becomes 2, right? Parent edge of 3 will be equivalent to the edge as 2, edge hash 2. So what we will do, we will enqueue 3. So we will enqueue 3 and the q becomes 5 comma 3 and the q becomes quite obviously 5 comma 3, right? So this is fine, I believe. Now we have 5 comma 3 and we will expand the node 5. So we'll be expanding the node 5. Again we'll visit the neighbor 4. So if you build that one, why we are visiting the neighbor, you will come to understand. So if you build or if you write it in the form of the diagram, so this one, the edges basically 1 to 2 they have given just in this way, right? So 1 to 2, 2 to 3 basically, like that they have given. So just give me a second here. 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6. Yeah, edges. So this one, let me come here. 1 to 2, 2 to 3, 3 to 4, 4 to 5 and 5 to 6, right? So here in this case we will we are expanding the node 5, right? So we will visit the neighbor 4. So this is unowned. Owner of 4 is 6 and the distance of 4 is 2 and the distance of 4 is 2. Parent edge will be 4 and which is equivalent to the edge hash 4, right? So we will be enqueuing the 4 basically. We'll be enqueuing the 4. So the q becomes 3 comma 4 this time. As we are enqueuing the 4, adding the 4, q becomes 3 comma 4 and this next what we will do, we will expand node 3, right? So here we got 3, we'll expand node 3, right? So the neighbor 4 is already owned, right? So previous step, neighbor 4 is already owned by the station 6, by the station 6. Just give me a second here somewhere, right? So this one, yeah, neighbor 4 is already owned by the station 6 basically, right? So this is fine. So we will skip this one. We will be skipping this one. We don't need this one, right? So result interpretation, let's go with the this one, result interpretation here. So parent edge used for the nodes 2, 3, 4 and 5 are the edges 1, 2, 4, 5. We know this one, right? So we have marked the used edges, that is 1, 2, 4, 5. The only unused edge is 3. The only unused edge is 3, nothing but 3 comma 4 here, nothing but 3 comma 4 here, right? So somewhere this one the unused edge is 3, right? So this one we haven't come across at all. So this one, unused edge is 3 and the only unused edge is 3 here, which is of the path 3 comma 4, right? So we can consider, so let's come to the conclusion that we can consider any edge that is not used as parent edge by the BFS forest can be removed. BFS forest can be removed, right? So that yields maximum removals while keeping every city within the distance d to the some stations. That's what they have asked in the question, right? So how many number of roads that can be removed, right? Along with that we have to what do we call display their indices as well. So this is fine, man. Now let's do one thing. Let's go with the final node details, right? So this itself we have discussed in the theoretical part. Let's see this one. You can just pause the video and look into it, right? So city, we have 1, 2, 3, 4, 5, 6. We have been mentioned 1 to 2, 2 to 3, 2 to 3, 3 to 4, 4 to 5 and 5 to 6, right? So owner station here we have, so this one 1 to 1, 2, 1, 3 1, and this one 4 6 6, and this one owner station I have given. So distance we have already written, right? I have showed that one step by step. Basically initially 0 1 2 2 1 and 0. The parent edges are so this one, for the 0 it's none, again for the 0 it's none, for the 1 it is 1, for the 2 it is 2, for the 2 it is again it can be 4, for the 1 it can be this one 5, right? So this one we had seen in the build as well. You can just look into the build and you can just say, right? So this is fine. Now let's move on with the used versus removable edges. So here edge index, so we initially we mapped that one to the indices, right? The edges we have mapped to the indices. First itself I had showed that one. So 1, so this one is mapped to 1 to 2, the same thing here. Again I'm showing the same thing here, right? So this one, just give me a second here, 1 second. So 1 we have mapped to the edge, this one 1 to 2, and 2 we have mapped to 2 to 3, and 3 we have mapped to 3 to 4, 4 we have mapped to 4 to 5, and 5 we have mapped to 5 to 6 connection, right? Basically, so this which is used as parent edge, so 1 to 2 we have used, 2 to 3 we have used, and 3 to 4 we haven't. So 3 is the only edge, right? So that wasn't used, right, as the parent edge. So this one we haven't used, right? So this is fine. And 4 and 5 we have already, right? So status is this one we can keep, and this 3 to 4, this is removable basically, right? So this is removable. So total final output is 1. So one road can be removed, this one road can be removed, and its index is quite obviously 3, right? So 3 is removable, as we got here. The maximum number of roads that can be removed is 1, and its index is 3, and I have said this can have the multiple answers, right? So we can have 1 and 5 as well. So I can just check for this, right? So for the approach that I went with, basically we get 1 3, right? So in the solution they have mentioned 1 5. That is also one of the correct answers. We can have the multiple answers. Don't get confused here. They have mentioned in the question itself. Now let's move on with the next part, complexity. So the time complexity is big of n, and the space complexity is big of n for the code that we'll be writing in the future, right? So why the time complexity is big of n here? So the time complexity is big of n here because reading n minus 1 edges, so we have to read n minus 1 edges along with the one multi-source BFS visiting each node and each edge a constant number of times. This is fine. So the total complexity would lead to big of n. So what would be the space complexity here? The space complexity would lead to big of n as well, because we are going with the adjacency lists plus arrays, right? So arrays of owner, distance, parent edge as well as used. So that's what I used in the approach as well, right? What are the arrays that we'll be using? Owner, so that itself I considered for the within the approach as well, right? Distance at parent edge as well as used, right? So this is fine. Also we'll be going with the BFSQ, right? BFSQ as well, right? So all of them are linear in n basically. So overall space complexity would lead to big of n. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n and big of n respectively, right? So now as we are completely familiar with the approach, we are good to write the code. Let's start writing the code. So let's start writing the code. I'll just come here. So first we'll be making use of the fast input and the output along with the different utilities, right? So I'll just go with here input java.input_output.star. Also let's go with java.util.star. So this is fine, man. So let me go with public class main. This is fine. So now let me do one thing. We'll be making use of the fast this one, man, fast scanner, nothing but the fast input, right? So this is customized. So this one is custom. Basically I'll just copy paste along with the edge. So don't get confused here. So this is purely related to the fast input and output, right? So that is the reason I have copy pasted. So this is fine. Now yeah, also I have this one. We have went with the edge here, class edge, right? So this is fine. This is purely related to the again input output, so that is the reason I have copy pasted, right? So you can just go with this one, the template of your choice. It doesn't matter, right? So this is fine. Now let me go with the main method. So this is fine. So here within the main, let me give throws exception, right? Throws exception. So within the main method, what I'll do, so I'll just go with a fast scanner, right? So I'll just go with fast scanner. We have already written this one plus fast scanner. This one we are making use of it, right? So I'll just go with the fs class. This one, what do we call variable name? So this one will be new fast scanner of system.m. And the thing is, so I'll just go with the print writer. So this one is out. It's new print writer of system.out. So this is fine. So the next step would be here. So we have to read the number of cities, number of police stations, and this one number of police stations as well as the maximum allowed distance to the police station. So that's what they have given, N, K, and D, right? So this one we have already discussed. This is related to the input output as well. So let me do one thing. I'll just give here N equals fast scanner dot. So I'll just go with the next int. So this is fine, man. Yep. Let me copy this one. Just come here, paste it over here, paste it over here. So this one will be N, K, also D, right? So I'll just come out of this one entirely. Now let's do one thing. Let's go with the array to store input station positions, right? So this one will be int stations raw. So I'll just go with stations raw. So that is equivalent to the, so we're just initializing, right? So this one will be new size k, whatever the k that they have given in the input, size k. So this one will be for int. Let's move on with the iteration part. I0, I less than k, I plus plus. So here this one I have considered the name stations raw here. Raw I, this is equivalent to the this one next int. So this one will be -1. This is fine. We are just reading the stations, man. So the next, let's go with the adjacency list for the tree. So this one will be array list of edge. So this is fine. Let me go with the variable g. So this one will be new array list of n. This is fine. So next, let's initialize the adjacency list. So this one will be for int I equals 0, I less than n. So this one will be I plus plus. So this one will be g of I, this one equivalent to, so let me go with the array list. Yep, we are just initializing the adjacency list. So this is fine. Next, we have to read each of the n-1 edges, nothing but edges indexed from 1 to n-1. That we need to do. Also, we have to read u and v. See, we have to read u and convert to that one to the 0 based. Also, we have to read v and convert that one to the 0 based, right? So let's do these three things. First, let's go with the iteration here, nothing but the for loop. So this one will be int I equals 1, I less than or equal to n-1. We are reading each of the n-1 edges, right? I'll just go with I plus plus. So within the for loop, we are reading u and v and converting that one to the 0 base. So this one will be int u equals fs dot next int. So this is fine. -1. So let me copy this one. Let me paste it over here. So this one will be u v. Yep. Fs dot next int -1. So this is fine. These two things are fine. Next, let's do one thing. Let's add the edge, nothing but from u to v with the index I. So this one will be g of u dot add new edge, this one v comma I, right? So next, let's add the edge from v to u with the index I, right? So this is undirected basically. We know this one, don't get confused, right? So this one will be add of new edge, sorry, so so this e has to be small actually, right? So this one will be u comma I. Yep. I'll just come out of this one entirely. So now what we need to do, so let's go with the owner node and as well as the distance node, right? So let's initialize that one. So this one will be, we are initializing owner node as well as the distance node along with the parent edge, right? So along with the parent edge. So this one, let me write this one quickly. Int owner equals new int of n. This is fine. So let me go with arrays dot fill of, let me pass owner here, comma, it's -1. Let me go with the dist here. This is equivalent to the new int of n. So let me go with arrays dot fill of distance comma -1. Oh, this is fine. Finally, let's go with the parent edge as well. So this one will be in parent edge. So this one new int of n. This is fine. Also, let me go with array list. So not the array list basically. Sorry, we have to go with arrays dot. We are filling, right? So I don't know why I give array list. So this is fine. This will be parent edge comma -1. So let me make this capital E, and also here as well the variable name. So here I'll just give parent edge. So yeah, now we are done with the this one, initializing owner of node, distance of node as well as the parent edge of node. So that's what we used in the approach as well. That is the reason I am using the same thing within the code as well, right? So that we don't this one so that it's not ambiguous, right? So this is fine. Let's move on with the further things. So now let's consider the queue for the multi-source BFS accordingly with the approach. If you remember the first step, so we will be going with the, we will be considering the multi-source BFS, right? So let's consider queue for it. So I'll just go with the, sorry, let me go with array dq basically. So this is of integer, this one is fine, equals new array dq. This is fine. Yeah. Now for int s of stations raw, right? So this one. So within the for loop, let me go with a simple if condition here. So we have initialized the BFS with every station city here. That's what we are doing with the for this one for loop basically. So now within the for loop, we have to handle the duplicates in the station list safely. So that's what we discussed in the approach. Let's write the simple if condition here. If owner of s, so equivalent to the -1, then what we need to do, a station owns itself, right? So the owner index will be equivalent to the node index here, right? So this one will be owner of s here. So this is equivalent to s. This is fine. And also the dist of s, so this is equivalent to the 0, and owner of s is equivalent to s, meaning station owns itself, and distance of s equivalent to 0 means distance 0 for the station nodes initially. And also we have to push the station into the BFS queue every step, at each step basically. So this one will be q dot add of s, right? So we are just going with the add operation here. Let me come out of this one entirely. Let's move on with the further things. Now let's go with the BFS loop, right? A classic BFS loop. So I'll just go with while. So not of q dot is, let's make use of the is empty operation as usual, q, right? So we are going with the BFS loop. Within the BFS loop, first thing here is, let's go with the current node that is popped from the queue. So this one will be int u equals, we'll be making use of the poll operation. So this is fine. The next step would be we shouldn't expand nodes beyond the distance d, right? So it may be pruning, keeps distance less than or equal to d, right? So that's what we need to do. So this one will be if distance of u, if it is equivalent to d, so let me go with a continue. We are skipping, right? So this is fine. The next step is we have to iterate neighbors of u. So I'll just go with the for loop here. This one will be edge e of this one g of u. This is fine. So within the for loop, so this one will be int v equals e dot 2. Yep, this is fine. Now let's go with the meaning if neighbors are not yet assigned to any station, then let's write that one first. Suppose if the neighbors are not yet assigned to any station, so this one will be owner of v if it is not assigned, right? If it is equivalent to the value -1, that is the reason we have considered -1 during the initialization as well, right? So then what we need to do, we have to assign the same owner as u first. So this one will be owner of v equivalent to the owner of u. So this one will be owner of human. So this is fine. Now we have to set the distance from the station. So this one will be distance of v equals distance of u plus 1, right? So the distance of u plus 1. The next step would be we have to record which edge was used to attach v into this one. What do we call we have to record which edge was used to attach v into the owner's tree. Also we have to enqueue v for the further BFS expansion. These two steps are left basically. Let me write that one. So this one is parent edge of v into considered e, right? E dot I'll just go with the index idx we have considered. So finally we have to enqueue v for the further BFS expansion. That's what we did if you remember, right? This is fine. Q dot add of v. Explore this node, every step that we got, we went with exploring node 2, node 5, right? So that's what q dot add of v here. This is when let me come out of this one entirely. So that's what we did in the approach as well. The same thing we are articulating in the form of code. Now let's do one thing. We need the boolean array marking which edge indices are used in the forest, right? So let's go with the initialization part first. So this will be boolean used new boolean of this one n, right? And here it would be for I equals 0, I less than n. So this one will be I plus plus, right? So let's go with a simple if condition here. Parent edge, so if parent edge of I not equal to -1, so this one will be used parent edge, so this one of I equivalent to true, right? So this is fine. So the next step is let's go with a list to collect the removable edges, right? So I'll just go with a array here, array list. So this one array list of integer. So this one I'll just go with a variable rem new array list. So let me complete the syntax here. This is fine. We are just going with a list to collect the removable edges, nothing but rem I have made use of, right? List to collect removable edges, right? So next let's go with the iteration part. We have to iterate all the original edges by index 1 to n minus 1. Again the same thing. If edge not used in the parent this one parent edge array, then it's removable. In our case the 3 was removable, right? So the 3 was removable. So that's what we need to do. The same thing we have to implement in the form of code. First let's iterate all the original edges by the index 1 to n minus 1. So this one for int I equals 1, I less than n minus 1, I plus plus, right? So the next step would be if not of used of I, so this is fine, null dot this one add of I. So this is fine, man. Yep. So let's do one thing now. Let's move on with the further things, right? So we have to print the number of removable edges and we have to print their indices in any order. First we need to print the number of removable edges. So this one will be out dot println this one will be rem size. So this is fine, man. Yep. The next step would be, let's move on with the further step. So we have to print their indices that can be of any order. Basically we can print their indices in any order, right? So let's move on with the iteration part. So this one for int I equals 0, I less than rem dot let me go with size here, so parenthesis as it is Java. So if I greater than 0, so then I'll just go with out dot print. We don't need ln, we have to print in the same line, so I'll just go with space here, right? So we need space as well, and let me go with out dot print here. So we have to get the value, so I'll just go with m dot get of I. This is fine, I believe, right? So let me come out of this one entirely. Now we are left with only one thing, that is we have to move to the new line. After removing the number of rows, basically we have to display its index as well, so in the new line. So let me go with out dot println here. This is fine. Yep, the final step would be we have to flush the output. So either we can go with out dot close, or we can just go with the out dot flush as well. I'll just go with out dot flush. So we are done with the coding part. So before checking the code with the different inputs, let me do one thing. Let me quickly copy paste the signature starter template over here. Just give me a second here. So here, let me paste this one. So I'll just come to the question. Let me copy this one. The output that we need to get here is 1,5. Let's check, or 1,3 as well, right? So both are valid. So here, yeah, I have forgotten this one, semicolon. Line number 83, 83, 83. Let me add the semicolon here. We have so many errors, man. Wow, 11 errors. So yeah, warning unchecked. Warning, let's leave the warning part here. Let's move on with the error basically. Cannot find the symbol. New edge I have given, line number 57. We come to line number 57. So this one I have given here g of u. 1 second. Dot add. This is fine. Oh, this edge has to this one e has to be capital basically. This is fine. Yep. Let me run this one again. Some errors are gone, I believe. 2 errors are gone. So now we have something here. Incompatible types int single array we have cannot be converted to the int basically, right? So int distance equals new int of, so which one? Line number 62 here itself, right? So int distance, there is, oh yeah, I have forgotten array here. Yep. Now we are having 3 errors basically. Uncheck. This is fine, man. Error. What is the error basically? I cannot find the symbol. Parent edge. So this e has to be capital. I forgot to change this one, I believe. Where is it? Line number 63. So yeah, here I am going with the capital E. Here itself you can see the variable name here. This is fine. We'll be left with 2 errors. Yeah. Cannot find the symbol again. Integer, this I has to be capital. And one more thing, line number 65. This is fine. This one as well actually cannot find the symbol. 65 and 93. 65, let me make this one capital I, and let me make this one as well 93. Let me make this one capital I as well. So let me run this one. Yep, we are getting the output 0. What is the output we need to get? 1 and 3, right? So let's check 1 3 or 1 5 basically. Let's check where we have done wrong. So what are the mistakes I have done here? I see in the line number 58, so I had copy pasted the same thing here. So this one has to be V here, right? So I forgot to change this one, I believe. So this one has to be V. So let me run this one. Yeah, we are getting 1 3. which is the correct output. Basically we don't have any problem, but still here also we have done certain things in the line number 88. So I have given here boolean, I have made use of the used variable, right? So this one, for the safer side, we have to go with the n plus 1 basically, right? Even n works in my opinion, but it is good to go with n plus 1. So let's keep this one n for now. If it doesn't work, let's change this one later. So in the line number 94, it's the better practice if you go with the n plus 1, right? So I just wanted to say that. And one more thing, in the line number 94, so we are going with I equals 1, I less than or equal to n minus 1. So I less than or equal to n minus 1 we are going with, right? So this is fine. I plus plus, this is fine, man. Let me run this one. Yeah, less than or equal to, because we are iterating all original edges by index 1 to n minus 1, 1 to n minus 1. So this has to be less than or equal to n minus 1, right? So this is fine. So I hope this works. So if this doesn't work, we can just go with the n plus 1 for the safer side. Let's see whether this works or not. So let me come here, we hit the submit button. We are getting the correct output, right? So we didn't check for the other inputs. Let's check for the other inputs as well. So we have one more input, basically output that we need to get here is 2 4 5. Let's check the same here. Yeah, we are getting the correct output, man. Let me copy this one, paste it over here. Let me hit the submit button. And one more thing, we are getting here for the previous one, we are getting 1 3, right? So we are having, they have said that we can have multiple answers for the same input, right? So we can just have the multiple outputs for the same input, right? So 1 and 3 also works basically. Accordingly, with our approach, we got the output 1 and 3 itself, right? So this is one of the valid ones as well. So we can just remove one road and according this one, and the index that would lead to 5 as well, and that index also we have to display, right? So that index would lead to 5. This is also one of the valid answers, 1 and 5 along with 1 and 3, right? So don't get confused. So this is fine. This is in queue. Let's wait for some time. I hope this works for all the test cases, man. Let's see. Yeah, I'm running on test 5 slowly. Yeah, the first thing is here, this part I copy pasted because this was purely related to the fast input output. Again, I'm telling you can just go with the template of your choice for the input output. So I have some templates that I use mainly, basically. So for the smaller questions, or for the first 3 questions, I make use of some templates, and when some of the questions require this thing, modular arithmetic, so when it is based on the trees, when it is based on the DP, I make use of different templates for different things, just for the optimization purpose, right? So I can just go with anything. So this is one of the simple templates as well. I have just went with the fast scanner, that's it. So this is fine, I believe. This is still running. Yeah, running on test 23. Let's wait for some time. Running on test 32. Yeah, this is pretty slow, man. So we have started the graph series. We are solving the advanced graph problems, right? So currently we are solving the problems on this one, graph, basically which are solvable by the BFS. This can be solved by DFS as well. It's easy with the DFS itself, but I want to go with the BFS. And if you have any questions that so this can be solved by this one, DFS and other this thing, yes, it can be solvable, but I find this one very much easily. I find it very easy to solve with this one, BFS. Basically, when it comes to solving the problems, DFS is the thing I would like to go with when it comes to trees, right? So when it comes to graphs, so BFS is the thing I opt basically. If it is solvable, or if it can be solvable with BFS, I would go with the BFS itself, right? So when it comes to trees, I prefer solving any problem with the most of the problems with the DFS along with the recursion, right? Everybody has their own this thing way of solving, right? So I'm not saying that you have to stick with me, so you can just go in your own way, right? So I prefer BFS if it is solvable by BFS, right? Then I prefer BFS over DFS when it comes to graph problems. When it comes to trees, again, I prefer DFS over BFS along with the recursion. So, yep. How many test cases are there, man? Running on test case 68. And this is going to be huge as well. So we will be solving 50 problems in the graph, right? So after this, I don't think I'll be solving this one. What do we call the competitive coding problems? This one, Codeforces problem for the YouTube. So this is going to be special, and this is going to be the last playlist, right? So let's solve this one by one. And one more thing, man, these graph problems are far better than this one, DP problems. I'm not gonna lie. So I can solve them easily. So all you have to know is so some of the algorithms, and this one, adjacency list and adjacency matrix, and this one, idea. So you have to have the idea how it works basically, right? So that's it. Some of the algorithms in the sense, so you have to know DFS, BFS, Digistras, so this thing, topological sorting, and some of the many this thing. There are many algorithms that you need to know, and some of them are very important. Those algorithms you have to know, right? So that's it. And comparatively with the DP, graph problems are literally this one easier. I'm not gonna say you will be able to solve at that point of instance. You'll be able to solve that completely, no, but comparatively with the DP, so this one, graph problems are more this one. It's peaceful to solve basically. I'm not gonna lie. How many test cases are there, man? Running on test case 135. Let's wait for some time. Yeah, you can clearly see here the verdict that we got here is accepted, right? So whatever the code that we have written works absolutely correct, right? For all the test cases, we have made use of the pure DP along with the pure BFS basically along with the Q. We are making use of the BFS, means we'll be going with the Q itself, obviously, right? So we are going with the BFS along with the Q to so we went with BFS along with the Q to solve this particular problem. I hope the solution part is completely clear, man, along with the approach and the complexities. For now, this is it. Thanks for watching, guys.